Welcome to this third video where the challenges related to changing the learning task in machine learning-based early decision making are discussed. This is the third in a series of 7 videos, which present the main ideas of the founding article of this new research field. Today, we open the log related to the learning task. That is, our objective is to deal with any learning task. But first, it is time to understand a very important notion, which is a non-myopa property. To begin with, let's put ourselves in the context of the original problem of early classification. Each time this is the case, you will see the small logo on the top right of the slide. As a reminder, the objective is to optimize the decision time, and for that, the triggering model considers two types of decision cost as input. The first one is the misclassification cost, which is very standard and indicates how much it costs to make a bad decision. The second one is the delay cost, which is added to the first one and which indicates the cost of making a decision late. These decision costs are expressed in the same unit, for example in dollars. For now, these costs are considered as input to the algorithm. But we will study the deep origin of this cost in the last video. What is the non-myopic property? To understand it, we need to place ourselves at the moment of using the model, at time t, when only a subpart of the input series is observed. A non-myopic approach is capable not only of estimating the cost expectation at the current time, but also of predicting this expectation for future time step, up to the maximum decision horizon denoted by capital T. Finally, a non-myopic approach is able to estimate at any time the best moment to trigger the decision in the future. Such an approach aims at estimating the future information gain, which will make the decision more reliable based on the beginning of the time series already observed. This slide presents an approach called economy, whose reference is given at the bottom of the screen. This non-myopic approach is formalized as follows. The function f estimates the expected cost of a decision at a future time, denoted by t plus tau. This first equation presents the cost expectation. We recognize the expectation of the misclassification cost, to which the delay cost is added since it is known in advance. Now, the cost expectation is developed in a very naive way, involving two sums. The first sum is done on the true class of the time series and involves the probability that the series belongs to each class. The second sum is made on the predicted class and uses the probability of being wrongly aware of the true class. The best triggering time, denoted by tau start, is defined as the minimum argument of the function when tau is varied up to capital T. Finally, the decision is triggered if tau start matches the current time, that is, the minimum of the cost expectation is located now. As presented here, this approach is not tractable. It cannot be exploited in practice since the true class is not available at the time the model is used. In the economy approach, there is a trick to make this formalization tractable, which consists in using an intermediate random variable, which is the membership of the series to a group. Thus, we have to build a data partition beforehand, and then the first term becomes the probability of belonging to a given group, conditionally to the subpart of the time series already observed. The other terms of the formula also become tractable. For example, the next term corresponds to the prior probability of each class in each group, and thus it can be easily estimated from the training set. Finally, the last term can also be easily computed since it corresponds to the confusion matrices of each classifier indexed by time, estimated within the considered groups. Finally, this trick is generic, and we need to answer the following two questions in order to design an effective learning algorithm. First, how to make the best data partition. Second, how to estimate the probability of belonging to each group. In the paper that is referenced here, many design choices have been tested in order to propose an efficient algorithm. The best design choices are to build a partition by discretizing the output of each classifier and to use a Markov chain model to estimate the probability of belonging to each interval at t plus 2. You can find more details in this paper, which show how this algorithm, named economy gamma, has become the best of the literature. The experiments in this paper underline the importance of the non-myopa property, which is in practice necessary to obtain the best performances. Let's go back to the topic of this video, namely the challenge of managing any learning task, not just classification. In our position paper, we proposed 10 challenges to the scientific community in order to develop this new research field. The first ones are related to the change of the learning task. First, we want to develop unsupervised early decision-making approaches, which keep the non-myopa property. Second, we have to formalize the trade-off between earliness and quality of decision in the case of unsupervised learning. The second challenge is to deal with other supervised learning tasks. Here are only 2 examples, and more details are available in our position paper. First, early extrinsic regression consists in estimating as soon as possible a continuous value from partially observed time series. For example, this time series could correspond to the heating inside a house, and we will try to predict the temperature outside. The second example is early forecasting. In this case, the trade-off between accuracy and earliness could take the form of a variable prediction horizon, which would adapt online. In cases where the continuation of the series is easily predictable, the prediction horizon could be far in the future. On the contrary, in cases where it is difficult to predict the continuation of the series, the prediction horizon could be reduced to few time steps ahead. Finally, the third challenge is to deal with tasks that belong to the domain of weakly supervised learning, which include many different settings where there are weaknesses in supervision. For example, semi-supervised learning is a famous case where only a subset of examples are labeled. B-quality learning is another very interesting setting where 2 training sets are available. The first one contains reliable labels, and the other one contains potentially corrupted labels. There are many applications of B-quality learning. For example, in cybersecurity, labeled data generally fall into 2 categories. On the one hand, there are few reliable examples which have been labeled by experts after an investigation. On the other hand, there are many potentially corrupted examples where the labels have been generated by rule-based systems. To conclude this video, we have identified the challenges related to the learning task and we have opened the corresponding log. In the next video, we will present the challenges related to the types of data. Thank you very much and see you soon!